So I'm Brett, and this is Max, and we're here to talk about our PHP JIT HHVM and how we added an LLVM backend to it. So a quick introduction. HHVM started in about early 2010. It initially had about 3 engineers, and then slowly added more over time. And since about February of 2013, it's been running every web server at Facebook, and it's open source. So if you go to hhvm.com/repo, that'll redirect you to our GitHub page, and you can see all the stuff we're doing and all of our code and file bugs and stuff like that. And our biggest open source user is Wikipedia. So if you have gone to Wikipedia since December 2014, you've used HHVM. They saw some pretty impressive performance improvements. I wrote a blog post about that back at the time. And we also have Baidu, Etsy, Box, and a few other major open source users. I think Baidu is actually bigger than Wikipedia, but they're mostly in China. So I expect more of you have used Wikipedia than Baidu. So one of the most common misconceptions about HHVM is people think we transform the PHP into C++ and build that. That's what we used to do before HHVM. So we had something called HPHPC, and that was exactly that. We would transform the PHP into C++ and then build that using GCC, and then that binary would run the site. But HHVM is completely new. It shares some of the runtime, but it's a pretty standard virtual machine with a JIT. The basic way that we get performance in a dynamic language like PHP is we assume that the inputs are going to be types that we've seen before. So if you have something like A plus B, and we've run that code before, and A and B were both integers, then we guard on the fact that they're still integers, and we can emit type-specialized code. And in this case, it would just be a single add instruction. So that can get some pretty good performance improvements. And we also have a static analysis pass that we run ahead of time. And this does some static type inference. So if you have a standard for loop, so like for I equals 0, I is less than n, I plus plus, we can usually prove pretty easily that for the entire duration of the loop, I is an integer. And in that case, we can eliminate the type guards. We also do some other optimizations, like we can prove that certain dynamic function calls actually always go to the same callee, so we can avoid the cost of a dynamic call. And the current performance state is that it's about 2 to 4 times faster than the current stable release of PHP. These performance numbers are using open source PHP frameworks like Drupal, MediaWiki, WordPress, things like that. And this link here has some more details on that you can go to once the slides are posted online. So this is a very high-level overview of what our compilation pipeline looks like. Starting on the left, we have our bytecode, which is HHPC. It's a custom bytecode format specially designed for PHP. And then the parts in blue represent what we have in the JIT. So first we take the bytecode and we transform that into HHIR, which is our main intermediate representation. It's high level, also PHP specific. And this is where we have optimizations like redundant ref count, elimination. We do some inlining, and we do other things like handling all the implicit conversions that happen in PHP. So if you have something like A plus B, if A is a string and B is an integer, then we want to coerce A to also be an integer. And that kind of stuff happens in HHIR. And then once we've done those optimizations, we go to VASM, which is our low-level IR. It's pretty similar to x86. For the most part, we have one VASM instruction for one x86 instruction. And this is where we do register allocation, and then we do the final code gen to x86. So to insert LLVM into this process, okay, PowerPoint is misbehaving, but pretend that the green boxes, the first green box on the left should say LLVM IR, and then the second green box should say x86-64. And then the blue boxes are HHIR and VASM. So the beginning of the pipeline is the same. We go bytecode to HHIR to VASM, and then we go from VASM to LLVM IR, and then we hand it off to the LLVM optimizer and code generator, and that handles the final x86 code gen. And the VASM to LLVM transformation is pretty simple because for the most part, one VASM instruction represents a single logical operation like addition or subtraction or a load or a store or a call. And it's already around the same level of abstraction as LLVM. So to get this working, we had to make a few major modifications to HHVM. The first one was how we handle PHP function calls. So the exact details of this are far too messy to get into here, but the main consequences of the way we used to handle PHP function calls was that we couldn't spill values to the stack across a call. This was because we have a PHP stack and a C++ stack in different points in memory, and the C++ stack has a fixed amount of memory allocated that's shared between all the frames on the PHP stack. And so we would spill to the C++ stack to keep the PHP stack in a format that's compatible with the interpreter. But this means that if we have 10 calls in the PHP stack, we still only have this fixed amount of space in the C++ stack. And so you just couldn't spill anything if you had a call because the callee could clobber your spilled values. The second problem was that if you make a PHP call, the callee can actually return out of the JITted code. It could go into the interpreter, it could translate some more code, and then it could eventually come back to the JIT. And the way we had things set up, it could resume in the original JITted code after the call, even though it had left the JITted code and gone on and done other things. So again, if you spilled something, did a call, and then the callee returned out of the JITted code, then all your values could be clobbered. So you couldn't store things on the stack there. And the final problem was that we didn't support catching exceptions across PHP calls. So this made a lot of our optimizations pretty bad. So basically when you get to a call, we know that this call can throw an exception, but we know that we also can't catch the exception in the JIT. So we can't sync any spills to an exceptional block or anything like that. So we basically fixed all of these. It took a few months, but we got our calls to a point where they act like a normal function call. So we can spill things. We have guarantees that when you make the call, it's going to return to after the call or throw an exception. And if it does throw an exception, we have a chance to intercept that and run some cleanup code. And the second major category of modifications was getting some x86 specific concepts out of VASM, our low-level ion. So I mentioned earlier that VASM was pretty similar to x86 because of the way it was born. And so we generally have one-to-one VASM to x86 instructions. This includes things like the IDIV instruction, which if you're familiar with x86, you'll know that it has implicit inputs and outputs in both RAX and RDX. And that doesn't really work with LLVM because everything has to be SSA. So the fix for this was pretty simple. We just created a higher level division operation with explicit inputs and outputs, and then lowering that to LLVM was simple. The second problem was that we relied on the fact that on x86-64, if you write to the bottom 32 bits of a register, it zeroes out the top 32 bits. And so if we had a 4-byte value in memory that we wanted to load and zero extend, we would just do a 4-byte load, relying on the implicit zero extension. And the fix for this was, again, pretty simple. All we had to do is make the zero extend explicit there. And then LLVM does the right thing. On x86, it just emits the 4-byte load because it knows about the zero extension. And then the final thing was endianness. So x86 is little endian, and we knew this when we wrote VASM. And so some of the things we did in VASM depended on this. And we discovered that if you write code that's little endian specific and hand it off to the LLVM optimizer, it can do some pretty strange things to the code, which is reasonable because we're not giving it code that isn't a valid format it expects. So we just had to find all the places where this is happening. And I think the canonical example of this is if you have an 8-byte value in memory and we want to inspect just the low byte, then we would just read a byte at the address of the value itself, which is fine on little endian. But on big endian, that doesn't work. So we would just load all 8 bytes and then truncate it to 1 byte. And again, LLVM did the right thing. It saw that we only cared about the low byte, and so it would only load a single byte. Okay, so now I'm going to go over some differences in the code generation we saw between LLVM and our backend. So on the left is the code from our custom backend, which I've labeled VASM, and on the right is the code from the LLVM backend. So as you can see, the code from our backend was quite a bit longer than what LLVM gave us, and that's even with 11 lines of code that I've deleted. So basically what's happening here is we're loading a value from memory, and then doing a whole bunch of adds and shifts and stuff like that, and then storing it back to memory. And you can see that LLVM, all it does is load a big constant into a register, multiply that by the value in memory, and then store the result back. And what's happening here was pretty straightforward. It was just recognizing that there was a series of like 15 different arithmetic instructions, and it realized that it could just fold them into a single multiplication rather than 5 adds and 5 shifts or something like that. And so this is a perfect example of what we were hoping to get from the LLVM backend. Because again, the optimizations to do this are pretty straightforward, and it's nothing that we couldn't do ourselves. But we knew that all of this, like there's all this engineering time and effort that has already gone into LLVM, and it seems silly to duplicate this stuff when we can take advantage of what's already been done. So this example is a little more complicated. You'll notice that the addresses of the instructions, I've renumbered them to be more easy to understand. These instructions are much more than 1 byte each. But again, the LLVM code is much shorter, and I'll highlight a few different parts of here to explain what's going on. So if you look at these 4 instructions from the VASM backend, you can see that we have a compare, and then a conditional set, and then a test, and a conditional jump. And this looks pretty silly. We wouldn't expect our compiler to output anything like this. It should just use the flags from the compare rather than funneling them through a Boolean. But if you look up here, you can notice that the instruction at address 9 actually has 2 predecessors. So it's testing one of 2 different values depending on which way we went through the code. And so we figured out that what LLVM did here was all it did was duplicate the test into each of the predecessors. And then in this case, when you have move a constant into a register, and then test the constant, and then do a conditional jump, that just becomes an unconditional jump. And for the previous one, this just becomes a compare followed by a conditional jump based on the flags from that compare. And so once you've done that optimization, the code gets reduced to slightly over half the size, and it's generally much better. Okay, so now these are some differences we saw in the code where the actual code would be too big to fit on a single slide. But one of the more common ones was large switch statements. So when we see a switch statement, if it has a lot of cases and they're dense enough, then we'll emit a jump table just like GCC or Clang would. But if you have sparse cases, then we just emit a series of if-then-elses. So if you have a 20-case switch statement, we'll just have 20 comparisons with conditional jumps. And we noticed that the LLVM optimizations were noticing this pattern and converting that back into a switch instruction. And then the code gen for that depended on how dense the cases were. But one interesting case was we saw that the code from VASM was maybe 20 lines, and the code from LLVM was much longer, maybe 30 or 40 lines. And what was happening was that it was using a binary search. So the resulting code was much bigger, but it looked like in the average case, it should do fewer comparisons to get to the final result. And the register allocator was an interesting one because we noticed that our register allocator was sometimes better, and sometimes the LLVM register allocator did better, where better means fewer spills. So there were some units we could compile without spills that LLVM couldn't, and some were the opposite, were the case. What we did notice was that LLVM was generally better at avoiding register-to-register moves, which usually indicate some failure on the part of the register allocator. And the final point is that basically everything about our JIT was designed to emit small code, because we found that iCache is the most precious resource for our workload. And so even if we need to run 20% more instructions, if those instructions are smaller, so like if we have a tiny loop instead of unrolling 10 iterations of a loop, that tends to be better overall. And so it was kind of difficult to get LLVM to emit code that was small enough for our needs. Max is going to talk about some of the tweaks we did to make that work. And that starts now.
Yeah, so Brett covered that we had what changes we had to make to HHVM. I'm going to talk about what changes we had to do to LLVM. And why did we have to do them? It's because we had to teach LLVM backend the tricks that our VASM backend was doing. And then we had to do tweaks and tunes to tailor it for our workload. our workload is characterized by very large code size and fairly flat profile, execution profile. So the first trick was fairly simple. It was introducing the new calling convention. There's not much new there. The register pinning technique was used before us. We had to pass our virtual machine stack and frame pointers in RBX and RBP. We also used R12 register for our thread local storage. And one relatively difficult thing to implement was to teach LLVM that our function is aligned. The stack at the function entry was a little different. And the reason for that is that LLVM function does not represent a PHP function, but only a part of it, a tracelet. So the prologue and epilogue is missing, and as a result, the return address is actually not there. So we have to do, when LLVM allocates variables on the stack, and when it calls other functions, it has to make certain adjustments. So once we implemented this, we had about 5 calling conventions used for PHP calls, for entering TC, exiting TC, for service requests, and also for C++ helpers. And we thought that 5 calling conventions were probably a bit too much, especially if you want to upstream. And we were looking for the ways to improve on it. And we came with almost universal calling convention when we use most of x64 registers to pass arguments and also to return. That worked fairly well for us. When we didn't want to use registers, we just pass undefined values, but we could basically pick any register from x64 and return in any number of these registers or pass arguments in there. This led to a reduction from 5 to 2 calling conventions, and this is what we have upstreamed. We have one calling convention used for PHP purposes, and another one to call C++ from PHP functions. The reason it's not a regular C++ call, we have to pass our virtual machine's frame pointer to every C++ helper because it needs to look at the state of the machine, and we use RBP register for that. Another trick that our VASM backend was doing, it was marking the call sites and telling the runtime to patch these call sites in the future. For example, you have a call to a function, the function gets re-optimized or optimized in the future, and you want to replace the destination. It's a performance optimization, but we were using it not only for performance purposes. Our correctness actually relied on it. In VASM, it was relatively straightforward. We were emitting one instruction at a time, so we knew we were emitting call. We record the site, we tell it to runtime. In LLVM, you pass a LLVM IR model to JIT, and what you get back is the code section. So we couldn't really disassemble the whole code section to look for the call sites. And the solution to this problem was introduction of location records, which act as markers in the LLVM IR that gets propagated all the way to assembly level. We also considered using patch points because and we actually used them at some point, but we found that we're not getting the maximum performance using this solution, and we don't need the overhead, or not overhead, but the optimization information provided by patch points. We also needed to support tail call optimization for our calls, something patch point could not do at the moment. And when we were not doing tail call optimization, we wanted it to be a direct call, not an indirect one. To implement location records, we used metadata. At the time, we are switching to perhaps operand bundles before upstreaming. But the first line shows the way it worked in LLVM version that we implemented it first. It was 3.5. So at the call side, you specify metadata and you attach an I32 value to it. And it gets propagated to assembly level. In the assembly, you'll see that several instructions will have this marker next to them. But also, during code generation, we write a special section, the LLVM locrex, which our runtime will read and identify the call sites. Let's see how it works. So we have a simple function call with locrec attached, and once we pass it through the code generator and output assembly, we can see that there are two labels for two instructions, and our assembly printer actually understood the locrec, so it will print them next to the label. And we found it useful not only for call instructions and invoke. We could attach locrex to any instruction, and it was useful when we were analyzing code. So we wanted to see, for example, what IR instruction resulted in which machine instructions. We attach a location record to it, and in the output we have all the data we needed. It was also interesting because what you see in LLVM IR is not what you get at the assembly. I think we ran into this several times. First time we noticed that we marked the call and we couldn't find the metadata. And what was happening was actually a dead code elimination kicked in and removed the call. So we didn't actually have to look for anything. And in another case, we had too much metadata. And we didn't realize we have to smash every call site because after tail duplication, you could get several calls for what was one call at LLVM IR. The format of locrec section is fairly simple. After the header, every record is represented as a label, then ID of the location record, and the size of the instruction. The interesting thing to note is HHVM is a multi-threaded application, so you can have one thread executing the code while the other actually wants to modify the destination of the call. And to make it not crash, we had to make sure that the call instruction does not straddle the 64-byte boundary, the instruction cache line size on x64. And this is something we had to convey to LLVM and teach how to generate sequences like that. And fortunately, LLVM already knew how to do that. It had the notion of bundle lines. At the time, they worked, I think, for the whole module. So it can make all the instruction fit within a certain boundary without crossing it. Didn't work quite well for us because the boundary was 64-byte and we cared about instruction size. So we modified it slightly so we can only set it for one instruction and then turn it off after. And this made sure that if the instruction was crossing the 64-byte boundary, we will prepend it with knobs and problem will be solved. The smashable call attribute was introduced. It only works with call and invoke instructions. And this is the same test case. As you can see, the same call instruction now is surrounded by bundle line mode directives. We faced another problem. We need to, the code generator needs to be aware about where the code is emitted and where the 64-byte boundaries are. And when JIT is writing the code, it does not where it will end up with. At the end, it will request a code section from the runtime with certain alignment. So the solution seems to be we had to request 64-byte code section. But this was too much code blowout for us. We actually, our other backend was packing functions very close together. There was sometimes up to 0 bytes between functions. We don't align at 16 bytes, which is typical for x64, we found that there's no performance difference, and we save a lot of space just by packing functions together. But our 64-byte boundary had to work, and we decided to use module flag called the code skew. And the way it works, before runtime calls JIT, it finds where the code section will be allocated. And it computes the skew to the alignment, the 64-byte alignment, and puts it as a module flag. So then when JIT is generating code, it's aware of this skew, and all alignment directives and bundle align directives will take it into account. And so after this, the problem was solved, and I think everything worked. Took us about 6 months since to modify both HHVM and LLVM. We had 80% of our code generated with LLVM backend. We were lagging behind in performance, about 10% at the time, which we sort of expected because we didn't do any tuning at all at the time. So our plan for the future was to increase coverage and try to improve performance. We started with looking at the waste of space that we've noticed while looking at the generated code. First, there was, I think, 20% of space we were losing just by having no data at all after every function. And it turns out that JIT wants to make sure that every relocation can go anywhere, and it reserves a special relocation stop space, which we never used. So we had to ask JIT not to do it for us. We added some interface, and a lot of space was saved with almost no effect on performance, I think, at the time. Then we also wanted our functions to be 1 byte aligned, or no alignment at all. But by default, unless you specify optimize for size flag, every function is aligned in 16 bytes on the x64. So we fixed that. And then we started fixing different problems while looking at the code. We thought there will be some major optimization that we could do that will give us at least maybe 5% performance back. We had high hopes for code splitting. But unfortunately, there was no silver bullet. What we had to do is probably implement about a dozen different things, and each one bringing back at most 1 or 2% of performance. We also noticed there was, for us, for our workloads, there was no difference between standard set of, or minimum set, I would say, of optimizations versus O2. And this was understandable because our tracelets, the functions from LLVM point of view, had very simple control flow. At the time, there were no loops at all. So I mentioned code splitting, and this is something our Wasm backend was doing for a long time. The overall performance gain was way more than 5%. And it was outputting code into 3 different blocks. The main code block, where most frequently executed code goes to, cold code contained blocks that were executed from less than 20% of the time, and completely frozen code, which is mostly error handling, exception handling, code that we didn't expect to execute at all. The effect of this optimization of code splitting is mainly on instruction cache and also on instruction TLB. And we had this optimization done at LLVM in a short amount of time, I would say, but we also had to add C++ exception support. This was somewhat way more difficult because there was a talk about C++ exceptions, and to modify the way they work and to make the function cover non-contiguous range proved to be very difficult with the current interface. Luckily for us, we had control over C++ exception runtime. So we were able to implement a couple of things to modify the tables in the way we wanted them to be, and also to modify our runtime to read the new information. So we got it working, but sadly there were no gains. And part of the reason is that we use huge pages for translation cache for our JIT code. So ITLB improvement was gone, and iCache improvement, I think we were already getting from splitting the blocks at the function level. So we were having hot blocks at the beginning of the function, followed by cold and by frozen. And it seems like it was enough for instruction cache. This was a weird optimization that probably wouldn't apply to anything other than HHVM. We returned from a tracelet with indirect call, because we don't have a return address on the stack, but we know where we have to return to. We have to issue a tail call. And the way we do it is a regular jump instruction, but when we enter a PHP function, we enter it via call. And when we enter via call but exit via jump, we upset the return buffer on the CPU. And the weird way to fix that was to actually issue push on the stack of the address and then a return instruction, which sounded strange, but it gave us 1.5% improvement, which meant a lot. So we cannot live without this optimization, but I can understand that it does not apply to many other cases. We did tweaks for code size just by looking at the code, at the generated code, and see what we can do. This is a fairly common pattern we have in HHVM, which uses ref counting. So we decrement the reference and check it against 0. About 5 instructions in IR. Load the value, subtract 1, store it, and do comparison against 0, and branch in the result. This resulted in 5 instructions, which almost exactly correspond to what we had in IR. But if you know x86 architecture, you can do way better. And to achieve this, we had to replace subtract of 1 with addition of -1. And this is the new code sequence. So just 2 instructions. And we solved this problem. But then we added more optimizations. And the same code sequence became 5 instructions again. We had to look at different optimization phases to make sure that the stars were aligned well to actually, even though the optimizations make it the right for us to instruction sequence. Another optimization that Wasm was doing, but it wasn't part of LLVM, was conditional tail call optimization. This is a very simple example where you have a C function calling or tail calling one function or another based on the condition. And very simple assembly code, compare jump to a label and jump to one function or jump to another function. But why do we have to do the conditional jump to the label when we can actually jump directly to the function? This is very, I would say, tiny optimization. It saves a little code size. It saves 1 instruction, but I wasn't sure was it beneficial in general. Was it, even though we had it in HHVM? So I decided to test it. I put this function in the loop, and I switched the condition every other iteration. I was interested, will we even see any difference? And yes, we did. The same code started running twice as slow as the original one. And it didn't make any sense to me. I did some investigation. It turns out we were really upsetting the prediction unit, the branch prediction unit on the CPU, because it turns out, in our case, the function that we were jumping to was allocated before the caller. And it was a back edge a conditional package, and I was flipping the condition every iteration. So, and branch predictor, I think it works in a way that it expects the loop to be executed many times, and we were actually fooling with it and got this 50% slowdown. Once I moved the function after the caller, everything worked fine. It was actually faster. But to implement it as a general optimization LLVM, or to enable it by default, would be difficult, taking that optimization could be not a real one. I think it's much better suited for things like LTO, which have the whole program view, or it could be done maybe at the module level. For HHVM, though, we could always guarantee that the functions, that the callees were following the caller. Brett, are you going to talk about the performance on the benchmarks?
So for our last couple slides, this is a quick view of the current performance of our LLVM backend. The blue bar is with LLVM off, the green bar is with it on. There's a very slight difference between the two, but it's actually within the noise for the measurements. And this is on open source PHP frameworks like MediaWiki, Drupal, and WordPress. On the Facebook workload, which is mostly what we care about, they're not measurably different. We have plenty of examples where the code from LLVM is smaller and better, but unfortunately it looks like that's not happening in the hot parts of the code, so it doesn't make a difference overall. And so we're currently not using this in production right now, because we need some kind of performance reward to justify the risk of turning something like this on in production. But we're hoping that we'll see improvements on this in the future. We didn't support compiling loops until very recently, so as the front end of our compiler gets smarter, we're hoping that the code we give to LLVM will look more and more like C code, that it can do a good job optimizing.
So we started upstreaming our changes to LLVM, or we have put in the calling conventions, and we plan to put most of the patches before 3.8 release, so this means sometime next month. We have our patches for LLVM 3.5 available on GitHub, so anyone can play with LLVM backend. Unfortunately, it wouldn't be on top of the trunk, but the idea is that once it's on top of the trunk, it will be much easier to do the tuning and improvements to optimizations and LLVM passes.
Right, and that's all we have. So these are some links with some more information about HHVM and the LLVM backend, and our IRC channels if you want to come bother us or ask us questions.
Okay, let's thank our speakers. We have a few minutes for questions. So we have a microphone over there for anyone on that side, and I'll run microphones on this side.
Hi, Richard Bagley. So very nice effort, and I see equivalent performance, but LLVM has a lot more to offer. And is there anything in the surrounding infrastructure that LLVM offers that you could exploit and hence?
I mean, like things that aren't strictly performance related?
Exactly, the tools, streamer classes, MC, all the sort of things that.
So I can't think of any off the top of my head. I don't know about you. So in the previous talk, they talked about how they can kind of record the compilation state of their GM or of their VM and play it back later. So we can dump the LLVM IR that we generated from our VASM. And like with that, it's easy to just save that to a text file and pass that to the LLVM compiler. And so for that part of the backend, it is really nice to be able to reproduce that and play around with LLVM optimizations. Unfortunately, the earlier parts of our JIT, we still can't do anything like that. So like we can print out a dump of our IR for debugging, but it's not in any kind of format that we can serialize and reload later.
So first of all, thank you for sharing your experience. It's been really interesting. One just observation I had is on the slide, one of the slides you had in there, you had a null check that would be a beautiful example of an implicit null check. You might want to look into that backend support. It might help you. We found the implicit nulls is a very material win for workloads that include lots of null checks.
Okay, take a look at that.
Thank you.
So the numbers that you were presenting were with LLVM 3.5?
Yes.
Okay. Have you gotten any numbers with LLVM 3.8? I noticed there was something on your slide, and I was just curious if there was any material difference.
Yeah, we reported patches to 3.8, and we saw a slight improvement, and mostly in instruction count, but performance was basically the same.
So you still have you have this VASM pass that's in there. If you fully embrace the LLVM backend, would that roll into the LLVM IR? Or are there certain things you do in there that wouldn't be able to be converted to like an LLVM pass?
Yeah, so theoretically, we could go straight from HHIR to LLVM. The main issue there is that HHIR is much more complicated than VASM. And so just like the code and the logic to translate HHIR into LLVM would be a lot more complicated.
Okay.
And so we found that even though the pipeline has more steps now, it's a lot nicer that we just go HHIR to VASM and then VASM to LLVM. So in theory, yes, but I think in practice, we'll keep things the way they are.
Thanks.
Any other questions? So I had one quick question. I noticed it seemed like you had a lot of very x86 64 specific stuff in there. Do you imagine like how difficult would it be to have it target like ARM v8 if someone else was using this, for running PHP and ARM v8 servers coming out, et cetera?
So I think for the LLVM backend part of this, it should be fairly straightforward. We don't really do, so like part of getting the LLVM backend working was getting a lot of x86 specific stuff out of VASM. And so there is some post-processing we do on the code that is x86 specific, but that's a pretty small amount of code. So it shouldn't be a huge amount of work to try and get the LLVM backend targeting ARM instead.
Okay, let's thank our speakers again.